Okay, so now we are going to derive the kinetic energy in relativity. Remember that the kinetic energy is defined as the change in kinetic energy equals the work done. Work is F dot ds, where s is distance. And so what we'll do here is we'll just say let's assume the initial kinetic energy is 0, so ki is 0, kf is k, so therefore we can simply say that k is equal to the integral of f dot ds. Okay. Where s is the distance variable, remember work is the integral of force dot distance, force over distance. Now, let's make, so far what we've done is nothing relativistic. This is all classical physics. F is dp dt dotted with ds. And if we're in multiple dimensions, it's a bit more complicated, but let's just do it in one dimension again. So in one dimension, in other words, everything is along the x-axis, then we can simply say that k is the integral of dp dt dx. One dimension, right, in the plus x dimension. Okay, so now we will go to the relativistic form of momentum, and we actually just did, in the derivation of Newton's second law, dp dt, we know that dp dt is the net force, right, so aside, we already showed that dp dt, which is the Newton's second law, the net force, is equal to gamma cubed ma. I'm going to rewrite that for the sake of being able to do this integral. I'm going to rewrite that as, in terms of u, so that we've got, yeah, let's just make sure. Okay, let's do it that way. So we've got 1 over 1 minus u squared over c squared to the 3/2, that's gamma cubed, times m times du dt. So now I've written dp dt in terms of u, which I'm going to go ahead and plug that back in to the kinetic energy formula here. So let's go to a new page and see if we can rewrite that. So rewriting this, we've got just plugging in for dp dt, plugging in the force, which is m du dt, over 1 minus u squared over c squared to the 3/2, that's just times gamma cubed, dx. So that's the force dot dx. Okay, so now we need to get this all in the same variable. So we can actually use the fact that u is equal to dx dt, right? We can use that fact to make a substitution for dx. Dx is equal to u dt, and so therefore the kinetic energy is the integral of m du dt over the parentheses, whatever's in the parentheses raised to the 3/2, times dx, which is u dt. Okay, then conveniently the dt's cancel. We've got a dt on the top and dt on the bottom, so that the kinetic energy is equal to the integral of m. Now I'm going to pull the u, this u over here, into there. So we've got m u du over 1 minus u squared over c squared to the 3/2. All of a sudden the integral's gotten a lot easier. At this point, I'm going to go ahead and put some limits on here, because we said we're going from the kinetic energy of 0. So kinetic energy of 0, now the integral variable is u, so it's where u initial equals 0 to u final equals u. So we're just going from 0 to u. So we're going to integrate from 0 to u. Okay. So I want to go ahead and do this integral. Just trying to memorize it before I go to the next page. Okay, so we've got k equals 0 to u m u du. Whoa, sorry, my computer screwed up. Mu du over 1 minus u squared over c squared to 3/2. Okay, so we need to calculate this integral. Sure, you could go and do it using some tool, but let's do the integral ourselves. We should be able to do derivatives and integrals as physicists. So we can actually do this integral just with substitution. I had mentioned by parts, but I forgot you can just do this with substitution. And the substitution we're going to do is taking a variable, just an arbitrary variable. Let's just call it z in order to do substitution and say that z is 1 minus u squared over c squared. If that is z, then therefore dz, right, doing substitution, integrating using substitution, dz is minus 2u over c squared du. So therefore, you can take this and say, oh, look, u du from what we just wrote down. So therefore, u du, right, that's this right here, u du. U du is equal to c squared dz over minus 2, or minus c squared over 2 times dz. This is a z, not a 2. Let's try to make my z's look like z's. Okay. So now I'm going to do all that substitution so that therefore k, on top we've got a u du. Now let's think about my limits later. U du, which is now minus c squared over z dz. And on the bottom, I've simply got z to the 3/2. All right, this now looks integrable. Looks like we can integrate it. Whoops, hopefully you caught my little error there because my 2's look like z's. This up here was minus c squared over 2, not minus c squared over z. So that means this here is not a z but a 2, so let me fix that. Okay, so now this is pretty easy integral to do. We pull the constants out, right? We've got minus mc squared over 2 times the integral of z to the minus 3/2 dz. Wow, the integral just became a lot easier to do. Okay, so the integral there is therefore k, and again we still have to deal with the limits. Actually, we're just going to substitute back in the u's so we can integrate from 0 to u. So I'm going to go ahead and do this integral minus mc squared over 2, integral of z to the minus 3/2, z to the 1 more power is z to the minus 1/2 over the 1 more power, which is minus 2. That's a 2. And right, it's limit, whatever limits that is equal from 0 to whatever z. Don't worry about it. Because we will go ahead and just backward substitute in the u so that k is equal to minus 2 over, minus 2, pull the minus 2 out front. That's a plus 2, the 2's cancel, so we've got plus mc squared times z to the minus 1/2, which is 1 minus u squared over c squared to the minus 1/2. And that's the limits there are 0 to u. Okay, so we just substitute back in for z. And so we're left with, oh look, that term right here, 0 to u, you just plug in a u here, and this term here is just a gamma. And so what's k? Whoops. Yeah, right. So got to be careful. Let me rewrite this on the next page. Careful. Rewrite this on the next page. Okay. So k is equal to whoops, what was it? mc squared. Okay, so we've got mc squared times 1 minus u squared over c squared to, my computer, to the minus 1/2 evaluated from 0 to u. So when we evaluate that from 0 to u, therefore, because that was the integral we had to do, we still had to do the evaluation, mc squared at u is 1 minus u squared over c squared to the minus 1/2, and then minus it evaluated at 0, and evaluated at 0, what do you get? mc squared. And now you can see that this is just gamma mc squared minus mc squared. Ta-da! That's what the kinetic energy is. You can also write that, we didn't do this in class, but you could write it as gamma minus 1 mc squared. But we like to write it in the form on the second to last line because, again, we identify the first term with the total energy and the second term with the rest energy. So the total energy minus the rest energy is the energy of motion, is the kinetic energy. Let's go one step further and just say, hey, look, let's show what it reduces to. Since we like doing math and we're doing math here, this is all fun math. And let's show that it reduces to the classical form when u is much, much less than c. So if u is much, much less than c, therefore, what does k look like? First of all, if we go to the 0th order, right, to 0th order, that means that gamma is equal to 1. If gamma is equal to 1, therefore k, right, gamma is equal to 1 only when u is equal to 0, then k is equal to 0, right? But, so how do we get to the 1/2 mv squared? Well, that's going to first order, right? So it's going to the first order approximation. We've got to take it out, take that binomial expansion out to one more place. So let's do to first order, to first order. Again, doing the binomial expansion, the very first term would just be 0, but the next term, let's see what the next term is. K is equal to, well, we got, for u much, much less than c, we got to show where u comes in here. We've got 1 over the square root of 1 minus u squared over c squared, mc squared minus mc squared. Okay, so I'm going to rewrite that as 1 minus u squared over c squared to the minus 1/2 mc squared minus mc squared. We can write that as, now we can do the first order binomial expansion, right? Doing the binomial expansion for u much, much less than c, either we just say this second term in the parentheses is 0, and we get 0, or we go out to the first order. And so we take the first order term, which is taking the 1/2, which is up here, and we put that down in front. And, right, so that the binomial expansion says that this is 1 minus 1/2 u squared over c squared. mc squared minus mc squared. Okay? So that's the binomial expansion, first order term. So we've got 1 plus 1/2 u squared over c squared, mc squared minus mc squared. Okay, let's go ahead and rewrite that on a new page. So we've got k equals 1 plus 1/2 u squared over c squared, mc squared minus mc squared. Okay, let's simplify that so that we get, well, now we can factor out the mc squared. So we've got 1 plus 1/2 u squared over c squared minus 1 times mc squared. So I just factored out the mc squared, and 1 minus 1 is 0, so we're left with 1/2 u squared over c squared mc squared. The c squareds cancel, and we've got 1/2 mu squared. Check. The kinetic energy simplifies to 1/2 mv squared or mu squared when the u is much, much less than c, so that we can go to the first order in the binomial expansion.